Welcome back. It's time for lesson 1-2, the properties of real numbers. Ding! Alright, so you're familiar with emoticons. Here are 6 emoticons. How can you describe a set that includes 5 of these, but not the 6th one? Oh yes, Charles. Let's see, emoticons that are not sad. Well, here's one that's sad, so we'd count him out. Are any of the other ones sad? No, I don't see any sad faces. This guy looks surprised, but that's not sad. So there's 5 that are not sad, 1 that is sad. So yeah, that works. Good job. Oh, Maria. Emoticons that are not wearing glasses. So there's 5 that are not wearing glasses and 1 that is. That's a good job too. Thank you for volunteering. So in algebra we deal with lots of numbers. There's lots of different kinds of numbers. For instance, the counting numbers, 1, 2, 3, 4, 5, and so on. We call these the natural numbers. Probably because you can look at something natural and count it like your fingers, 1 finger, 2 finger, 3 finger, like that. So those are the counting numbers. If we include 0 in our set, now it's not the natural numbers anymore. Now we call it the whole numbers. So maybe one way to remember is this one has a hole in it. Another way to remember is you can count whole things. And it is possible to have 0 things, right? You can open up your cupboard and have 0 cans of pineapple. That is possible. Or you can have 1 can or 2 cans or 3 cans. So those are the whole numbers. Then if we also include the opposites of all the natural numbers, so we have positive natural numbers, 0, and all the negatives of the natural numbers. Now these are called the integers. The integers are the natural numbers, their opposites, and 0. Then in between these whole numbers, these integers, there's a bunch of different little decimal numbers. And most of them, a lot of them, are what we call rational numbers. Rational numbers are numbers that can be written as a ratio of 2 integers. So any decimal that is repeating or terminating, so it counts as a rational number. Then we've got irrational numbers. These are numbers like pi, which is like 3.14159 blah 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 forever. It keeps going forever, but it never repeats. So we can't write that as a ratio of 2 integers. And square root of 2 is going to also be a decimal that goes on forever but doesn't repeat. And basically any square root that doesn't come out even, like square root of 4 equals 2, that would be, so square root of 4 would be actually it would be all of these over here. It would be a natural number, a whole number, an integer, and a rational number. But square root of 2 doesn't come out even. It's like 1.4 something 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 forever. So these are called irrational numbers. Rational numbers are all the numbers that you can write as a quotient of integers. A over b, where b doesn't equal 0, because you're not allowed to divide by 0. It includes terminating decimals. For example, 1/8 is 0.125. And you can also write that as 125 over 1,000, which would reduce to 1/8. It also includes repeating decimals, like 0.33333 forever is the decimal for 1/3. And 1/3 is rational, because it's 1 over 3. Irrational numbers have decimal representations that neither terminate nor repeat. So 1.414213 da 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 da, it never repeats. And they cannot be written as quotients of integers. Alright, so we classify variables by naming the subset of the real numbers that gives you the most information about the numbers that the variable could represent. What does that even mean? Well, let's look at a problem. Maybe that'll help us understand that. Your school is sponsoring a charity race. Which set of numbers does not contain the number of people, P, who participate in the race. So the question is, what kind of numbers can P take on? What kind of values can P take on? Can it be 0? Well, if it's 0, then there's no race. So what's the point in counting 0? If we count 0, then we're counting the possibility that this race doesn't even happen. So we're going to ignore 0 for now. What about 1? You have one person in the race? Yeah, you'd be guaranteed to win, but it wouldn't be a very interesting race, maybe, but it's possible. You can have 2, 3, 4, all those natural numbers. You can have those in the race. What about which? Let's see. So the question here is, which set of numbers does not contain the number of people? So the number of people is going to be these natural numbers, right? Well, does integers contain the natural numbers? Yeah, it has negative numbers, it has 0, and it has the natural numbers. Do rational numbers contain the integers, or these positive integers, these natural numbers? Yeah, rational numbers just means that you can write it as a fraction with 2 integers. So you had 7 people in the race, you can write that as 7/1. So the only one that doesn't count is irrational numbers. Irrational numbers does not include numbers like 5. Square root of 5 maybe, but you're never going to have a race with the square root of 5 people in it. So the answer to this one is D. So which one, but to ask a different question, which one of these best represents, how would we classify the variable P? We would classify P as being a natural number. Okay, go ahead and pause the video and see what you think about this question. All right, so if each participant made a donation, we would have a sum of money that either ends in a whole dollar amount or in 50 cents. So what subset of real numbers best describes that amount? We can have $15.50, or we can have $31, or we can have $46.50. It's either going to end in 50 cents or in an even dollar amount. So what numbers do the natural numbers work with that? No. The natural numbers don't work with that because they're just 1, 2, 3. There's no decimals there. Integers? No, because the only difference between natural and integers is the integers have 0 and they also have -1, -2. Well, we're not going to have those. What we really need is we need rational numbers. Rational numbers include all these decimals that are terminating, and these are terminating decimals here. All right, so graphing numbers on a number line. What's the graph of these numbers? -5/2 is, if you change that into a mixed number, that's -2.5, which is right about here. The square root of 2, if you were to punch that in your calculator, 2 square root, it's about 1.41. So that's right about here, a little less than halfway. Right at halfway would be 1.5, so 1.41 is a little bit closer to 1. 2.6 repeating, that's 2 2/3. So that's going to be 2/3 of the way between 2 and 3. All right, go ahead and pause the video and see if you can graph these numbers. All right, so the square root of 3 is approximately 1.7. So 1.7 is going to be right around here, more than halfway between 1 and 2. -1.4 repeating. Well, -1.5 would be here, but not quite halfway, so right about there. And 1/3 is 1/3 of the way between 0 and 1. And at this point, I should mention that the secret phrase for this lesson video is hornswoggled. So how could we put real numbers in order? Well, one way to do it that's kind of helpful is using a number line. And if we're comparing a square root to a decimal, one good thing to do is to pick a square root that's really close to this that comes out even. And we're pretty sure that the square root of 16 comes out even. Square root of 16 is 4. So I'm going to say here's 4, which is the square root of 16. So 17 is greater than 16, so that means that the square root of 17 is going to be a little greater. And then 3.8 is a little bit less than 4. So we got a few relationships here. Well, here's our 3.8, and here's our square root of 17. And we know that if you're to the left, you're less than. So 3.8 has to be less than the square root of 17. So by using the square root of 16, it gave us a reference point between these square roots and these decimal values. Alright, so go ahead and pause the video, take a look at this question, and go ahead and hit play when you feel like you know the answer. So if we want to compare square root of 26 and 6.25, we might want to compare them using the fact that the square root of 25 equals 5. And I like to do number lines because they're fun and pretty. And I happen to know that 5 is the same thing as the square root of 25. The square root of 26 is a little bit bigger than the square root of 25. And then 6.25 is, let's see, this is 6. Then 6.25 would be over here. Well, what is 6 is the square root of 36. So I know that the square root of 26 is less than 6, and 6.25 is bigger than 6. So now I can see that 6.25 is bigger than square root of 26, or in other words, the square root of 26 is less than 6.25. Alright, so if A, B, and C are real numbers, such that A is less than B, so that means that A would be to the left of B, and B is less than C, so that means B is to the left of C. How do A and C compare? Well, A has to be then to the left of C, so A would have to be less than C. That's actually called the transitive property. So properties of real numbers are these relationships that are true for all real numbers. Except in one case, it's not true for 0. Mostly because you can't divide by 0. You always get exceptions for 0. So the opposite, or additive inverse of any number, A, is negative A. And we call it the additive inverse because when you add them together, you get 0. And 0 is what we call the additive identity, meaning you can add a number and its inverse together and get 0 every time. Examples, 12 plus negative 12 is 0. Negative 7 plus 7 is 0. The reciprocal, or the multiplicative inverse, of any non-zero number A is 1 over A. And one way to tell if two numbers are multiplicative inverses is that they multiply to equal 1. The product of a number and its reciprocal is 1. And 1 is what we call the multiplicative identity. So for example, 8 times 1/8 is 1. Negative 5 times negative 1/5 is 1. So some properties of real numbers. If A, B, and C are real numbers, we have the closure property. Closure means that if you do addition to two numbers in this set, meaning real numbers, the set of real numbers, that the answer is also in that set of real numbers. So closure over addition means that if you add two real numbers, the sum is also a real number. And for multiplication, if you multiply two numbers, the product is also a real number. The commutative property means that these numbers can commute. Just like driving to LA and driving back. It doesn't matter which position you're in, you're still driving on the freeway. So a plus b is the same as b plus a. Just like 2 plus 3 is the same as 3 plus 2. They're both 5. And it works with multiplication too. 2 times 3 is 6. 3 times 2 is also 6. So the multiplication and addition both have the commutative property. The associative property says that we can group things differently. Here we grouped a plus b together, and over here we grouped b plus c together. Same thing works with multiplication. The identity property, that any number plus the identity equals itself again. 0 is the additive identity. 1 is the multiplicative identity. So 0, you can add 0 to anything and you get the same thing back. And 1, if you multiply anything by 1, you're going to get the same thing back. The inverse property is if you add the opposite, you get 0. And if you multiply by the reciprocal, you get 1. And then you're familiar with the distributive property where a gets multiplied by this sum, b plus c. You can distribute the a times b plus a times c. All right, so which property is this? Here I got negative 2/3 times negative 3/2 equals 1. Got two numbers multiplying to equal 1. And that is the inverse property of multiplication. All right, what's happening here? The grouping symbol, the grouping doesn't actually change. 5 is on the outside, 5 is on the outside. What changed is 3 and 4 swapped positions. They commuted. So that is the commutative property of multiplication. Go ahead and pause the video and see if you can figure these ones out. Go ahead and hit play when you feel like you got it. Okay, so for A, all we did here was we distributed the 3 through. We got 3g plus 3h plus 2g. So that is the distributive property. All right, use the properties of real numbers to show that A plus the quantity 3 plus negative A equals 3. Justify each step. So justify each step means say what property we used. So the first property I'm going to use is the commutative property of addition. And that says that I can add in either direction. So I'm going to change the direction of this addition. Instead of 3 plus negative A, I'm going to call it negative A plus 3. Next, I'm going to use the associative property of addition to say that instead of grouping these two together, I can group these two together. So A plus negative A plus 3. And next I'm going to use the inverse property of addition to say that A plus negative A equals 0. And then 0 plus 3 is 3 because of the identity property of addition. All right, so now we've shown that it equals 3. And that is the end of the lesson. Go ahead and work on the practice, get that formal write-up going, and I'll see you in the cyber world. Bye-bye.